Yeah.
Fantastic. Okay. So this talk is about polynomial regression, and with a brief, with sort of an application to learning dynamical systems. And I'll sort of explain what that means shortly. So let's dive right into it. So what is polynomial regression? It means we try and fit a polynomial to data to make predictions as to what it is. So given data, we try and find a function, a polynomial function that basically allows us to predict values given an outputs given a data point, right? That's standard. So now we all know the problems with polynomial regression. Have you guys ever tried fitting a high degree polynomial to data? You know that it doesn't really work out well at all.
Yes.
We have already fit neural networks, right?
Yeah, but so I'm going to go into why polynomials are might be nice, because anyway, so you'll see why these things are useful. So what we're going to talk about is something called shape constrained regression. That means, you solve like a least squares regression problem, but you add constraints that basically say this is what the shape of the curve will look like. So so basically you have some a priori knowledge, some domain knowledge of what kind of functions you expect to see. The mapping from your data, from your inputs to your outputs, what do they look like? So that's what shape constrained regression tries to do. And until now, this paper from these guys at Princeton, this is not something that's really been done in the polynomial setting because, quite frankly, nobody's thought of using the tools that are available together, right? So to begin with, let's talk about unconstrained polynomial regression, and it looks, and we'll see what it is. So what we're doing is given data X with the labels or outputs Y, we want to find a polynomial P star of degree at most D, and we have to decide a degree D, because that tells you how many parameters you have to solve for. And of course, your variables are in Rn, which basically satisfies this least squares optimization problem. So over here, what's going on? We're actually solving an optimization problem over the space of polynomials, right? As you can see over here, this is the argmin is over the polynomials of degree less than D, correct?
Yeah.
Right? So now why is it that we can solve this? Well, the key trick here is that we know that polynomials are linearly parameterized in terms of the monomials. So we know that Z is like, here Z is a vector polynomial. So if you take n is equal to 2 and D is equal to 2, this vector will be 1, x, y, y squared, x, y, x squared, right? So that's all the monomials in two variables of degree 2, up to degree 2. Right? So you can sort of expand that and imagine that for however many variables and however high a degree. So now, as we know, a polynomial is a linear combination of monomials, so you can write it in this inner product format. And so every polynomial of degree D is uniquely parameterized by this vector Q, correct?
Mm-hmm.
Okay. So now this allows us to solve this problem using sort of a standard least squares sort of technique. So we write P of x in this Q transpose Z of x D, and then we just find we have now to solve for this vector Q instead of solving over the polynomials. So now P star is basically given exactly by Q star, right? Uniquely by Q star. So Q star is the solution to this optimization problem. Okay, this equation 2. Right, so this is, now this looks much more familiar, right? This looks like a standard least squares problem, except instead of x transpose Q, it's Z of x D transpose Q. But because we have the data points, these are all constant vectors. So much like the standard least squares, the polynomial least squares is Z transpose Z inverse ZY, which is exactly the same as the standard least squares, except in least squares it's x transpose x inverse XY, right?
Correct.
So this much is standard. Now the problem is, unlike the linear least squares regressor, this doesn't necessarily give us anything really useful. For example, the linear regressor always has a lot of really nice properties. It's convex, it satisfies the minimum L2 norm, all kinds of good stuff is there, right? But with this, we really don't get any such guarantees. So now how can we give ourselves guarantees on the kind of shape that we want our regressor to have? Well, we simply add polynomial constraints, okay? So what does that mean? So we add constraints to the polynomial optimization problem initially, simply like this. So like P star of x is argument over the polynomials, given this least squares cost, such that P of x is convex. And so this is standard. And the way you'd want to enforce this is by saying the Hessian of P is positive semi-definite for all x in omega, right? Because the Hessian of P now will be a polynomial matrix, like a matrix where every entry is a polynomial. Is that clear?
Yes.
Right? So now the bounded derivative thing is a really nice trick because now you can enforce things like monotonicity, Lipschitz smoothness. So for example, here you have this del P by del Xi lies between Ki minus and Ki plus, right? Now, if those are equal over all I, Ki minus equal to K plus, or Ki minus equal to minus K plus for all I is equal to, absolute value is equal to some K, then you can see this is actually the K Lipschitz condition, right? And so a great many constraints can be enforced with this. So coordinate-wise monotonicity over the of the entire function, Lipschitz smoothness, all of these things can be enforced with this condition. So it's a very powerful sort of thing to do. Mm-hmm. Now, again, we're back at the problem where we have to try and optimize over a space of functions, right? So that's hard. We don't have an algorithm that can do that, right? So this is the kind of the hurdle that we have to overcome. Okay.
So one quick question. So you're saying how to solve these problems means exactly?
No, it's approximate. Generally speaking, there are situations where a solution is exact, but I'm not going to go into that because that goes into complexity theory and decidability, and I don't have a handle on that.
Okay. No, but so if I understand correctly, so essentially a shape constraint is more or less like some form of a regularizer that you are adding on your cost,
you
right?
You can think of it like that, but it's more explicit than that, right?
Okay.
How do we, what does a regularizer do, right? A regularizer is basically taking the Lagrangian, instead of minimizing your original cost, you're minimizing, in a sense, the Lagrangian, right? That's why you have that lambda over there.
Yes, yes.
Right, so this is more explicit than that. Here I'm saying, look, P is convex. Here I'm saying my partial derivative of with respect to xi lies between this and this, right?
Okay, yes.
So that's kind of what I'm trying to, so it's more explicit than that. And because it's more explicit, it also gives us a little more flexibility to play around with it. Okay?
Okay.
So the key idea is this idea of sum of squares programming. So if you guys would recall, in Atimoto had given that talk maybe some 4 or 5 months back on S-word programming. So the key trick is to say that, look, I have a polynomial P of x. It is non-negative. How do I test that? Well, I can't. That's actually a strongly NP-hard problem. But I can test whether it's a sum of squares, which is tractable. Okay, so now I relax this constraint of P of x is positive to P of x is sum of squares. Okay. Now, why is this tractable? Well, so there's this theorem, which again I proved in that earlier talk. P of x is sum of squares is equivalent to saying there exists a PSD matrix such that Z transpose QZ is positive. Or rather, actually, this is not correct. Z transpose QZ is equal to P. Of course, it's positive. It's by definition, it's positive. This is a typo. 6 should be, instead of greater than or equal to 0, DXD transpose QZ should be equal to P. Now, what this is, Q are your decision variables, and the coefficients of P are your decision variables, right? Mm-hmm. So this becomes linear in Q, the entries of Q and the coefficients of P. Because recall, we can write P in this form, right? Q transpose Z, right? Mm-hmm. So now we can write this will become something in Q transpose Z x2D, right? So now we just have to equate those coefficients. And whenever there's 0, that's it, right? So this is of degree 2D. You can expand this out. You'll get something in that's linear in the entries of Q. And you equate those two together with this constraint that Q is greater than 0 is PSD. And that solves your problem for you, right? So this is now convex. This is a convex problem. These constraints are convex. Interior point algorithms solve this problem in O of n cubed, where n is the number of variables. So this actually is not n in terms of the size of x, but n in terms of this value k over here, n plus d choose d. Okay, so that's basically the trick that we're going to employ over here. Now we have to go one step further. So what we have is that result is for the global case. There's no constraints that we can add to it. But now let's say we have a semi-algebraic set. So some GJs here are polynomial. So this Rx basically is the set of polynomials in X. Okay, so that's just a notation, right? So omega, this is a set that's defined by GG of X is non-negative, right? And so we are constraining X to this subset now. So let's say this becomes, we have these two theorems that we're going to use extensively. So a polynomial is non-negative for all X in this omega if you can find sum of squares polynomial. So that's like x squared plus y squared, x plus y squared, x squared plus y whole squared, that kind of thing, right? Such that P of x is equal to sigma 0 plus sum of Gj sigma j. Okay, so this is a very powerful result. And these two statements are equivalent. And you can extend this to matrix polynomials as well. So we have this matrix polynomial h of x is positive semi-definite for all x in omega if you can find these sum of squares matrices, which basically means that if this h of x is equal to s naught plus sum of gj sj is these two things are equal. Now we say a matrix is a matrix polynomial is sum of squares if, let's say, S0 of x, right? S0 of x is sum of squares if y transpose S0 of x y, where y is also an Rn, is a sum of squares polynomial in 2n variables. Okay, so you have like something, your matrix may be an x1, x2, then you have the polynomial y transpose h of x1, x2, y is equal to some polynomial in x1, x2, y1, y2. If that polynomial is sum of squares, then we say that S0 of x, let's say, is a sum of squares. Right? So these constraints are also doable with this kind of the same kind of machinery. Okay, now we can rewrite these programs using that same trick. So for the convexity case, we have this. You're solving this least squares program such that the Hessian is now positive for all x and omega. Now we change that to this constraint, right? So such that the Hessian of x minus this term here, this sjgj is a sum of squares, right? And that comes from the previous thing because we just moved the sum over j to the other side. So h of x minus gj sj is equal to s0 is exactly the same as saying Hessian of p minus sjgj is a sum of squares polynomial, right? It's exactly the same thing. So now this is tractable. This is now convex. This can be solved with an interior point program with the quadratic cost. Very doable. Right now, the same thing we can do for the bounded derivative case. You have p star is equal to the argument of blah blah blah. So we search for over a polynomial p these sum of squares polynomials sj rj, and same cost. Except now we have these constraints over here. So we want ki minus del p by del xi for all i's. Oh, there should be an extra subscript over here, sigma ji gj. Oh, it's a typo. That should be sj and this should be rj. Sorry, it's a typo. sji rji. But yeah, so this should hold for all i's. And now again, this is a convex intractable program. Okay, so this is how now we can do a great deal more than we could before. And this solves problems like, that crazy overfitting, stuff like that. Okay. Now, so the question now becomes, how good is the SOS approximation? So we see, so if you recall, this is the original functional optimization problem. 4 is just finding a P that's convex. So GMD is the degree D solution to 4 with M data points. D bar is the SOS relaxation. H is the bounded derivative case. H bar is a degree D solution. Okay. So for all F, in C2 RNR such that this holds. Okay, this is our formulation. We have a function f that's twice differentiable, and the outputs of yi is equal to f of xi plus mu I, which is a zero mean bounded variance random variable. They're independent but not necessarily IID, because the variances can be allowed to vary. And we see that the support of the data points that we have, or should be bold xi's, is some box. Okay. Now we pick a full dimensional subset of B. So, like, let's say the convex hull of all the xi's. Now, what they prove in the paper is also a very lengthy proof and relies on sort of these complexity results. Is that as your data, the number of data points and the degree of your regressor polynomial goes to infinity, all of these problems, right? The error goes to zero. The worst case error goes to zero. So that means you get the more data you have and the higher degree you get perfect generalization. And of course, what you can also do is you can find, if I pick a generalization error delta, I can get bounds on M and D. But unfortunately, I don't have a handle on those proofs because they're a little bit beyond what I've learned so far. And so what's interesting is also that this result can be applied to the case where we choose a piecewise smooth polynomial regressor as well. And it's a simple application of this positive Snellen-Sachs result. You just pick your domain of where each sort of slab of the regressor holds, and you can extend it to the piecewise smooth case as well. Now, so that's sort of the general idea of shape constraints, right? So this is clear, like, and the thing is, this result, this theorem, is kind of obvious, right? If you have an infinite degree polynomial, that's basically saying you have an infinite degree Taylor series, right? Which, as we know, approximates the polynomial exactly. And if you have infinitely many data points and a polynomial of infinite degree, of course, you're going to get perfect approximation, right? Okay. There's no real question about it. It's very intuitive. So the drawback of this is that this entire result is using a great deal of math to say very little. Is that clear? You guys got it so far?
Yeah.
Okay. So now,
but it does not say anything about the generalization of the shape constrained polynomials answer, like the output.
Yeah. No, this is the shape constrained polynomial answer. So this is the SOS relaxation. So what's nice about this is it's saying that an infinite degree SOS relaxation, as you increase the degree of your relaxation, and as you increase the number of data points, your generalization error will go to zero because you're exactly replicating the function.
Correct.
Right. So it's not just saying that you can find an exact polynomial. The solution to the relaxed optimization problem is the same. But again, this also it basically borrows a great deal from existing literature on how well sum of squares relaxations to optimization, polynomial optimization problems approximate the exact solution. And the truth is that as you increase the degree, it's been proved before that you will exactly reach the true solution to any optimization problem. Yes. So this is why. So this is basically it's almost a corollary to that, but it takes a bunch more extra steps. So it's not really that interesting. So just a second. So the next question is, where is this really applicable? So the nice paper, the other paper, which didn't have proofs, but the shape constrained regression for learning dynamical systems is a very useful trick for this. So as you know, we won't necessarily have perfect models of dynamical systems. So are you guys familiar with what a dynamical system is?
Yeah, I think the PID kind of a.
No. It's any system that is modeled by a differential equation. Okay.
Yes, that depends on time. That changes with time.
Yeah, exactly.
Yeah.
Exactly. So we may not necessarily have perfect models, but we need models for control, right? We need to control these systems, whether or not we have the models. That's actually a better way to say it. So think of the walking robot, think of, a PID controller for a drone, think of any number of things. Think of, an autopilot for a plane, making sure it flies stably. All of these things are control systems for a dynamical system, right? So there's two sort of extremes, right? One is when you have a perfect model that we can't do, but if we don't have a model, there are two other extremes. One is a pure model-free approach, which is just pure RL, an unobservable MDP, just use policy gradient and go for it. And the other approach is system identification, where you try and learn an approximation of the dynamics, which is learning the system. Okay, so this is really well studied in the linear case, where x dot is equal to a matrix A multiplied by so x dot of t, dx by dt is equal to a constant multiplied by x of t. This is very well studied. In the nonlinear case, it's a lot more difficult. Okay, so shape-constrained regression really allows us to approximate nonlinear vector fields well. And this is where we take side information, what the paper calls side information, and what those really are is exactly shape constraints. Right? So these two things are kind of equivalent. So the paper discusses 6 kinds of side information. First is interpolation at a finite set of points. So that's like saying f of 0 is equal to 0. F of 1 is equal to 10, 1. Right? So f of 0, 0 is equal to 0, 0. F of 10, 1 is equal to, 1, 20, or whatever it is. Right? So the next is sign symmetry. So if I have this sign matrices with plus or minus 1 AB, f of ax is equal to bf of x. Again, this is a polynomial constraint, except you have n such constraints. Coordinate non-negativity, these 3 and 4 are exactly the same, coordinate-wise monotonicity. This is, in fact, exactly the bounded derivative case, right? Right? So you're saying that the derivative is between 0 and infinity, or between 0 and minus infinity, or between minus 1 and minus infinity. Right? So this is exactly the same as the bounded derivative constraint. This is slightly simpler. Instead of the derivative, I'm just saying that the function itself is, so p of x itself is between 0 and infinity. Right? So set invariance, so that's saying, let's say I want to be inside some set defined by these polynomials hi. So this is an old result. So we're saying that if this is invariant, then for all hi of x that is equal to 0, this inner product term is positive. Oops, and the right bracket should be inside the inequality. But anyway. Yeah, there's something called Hamiltonian vector fields, which basically has certain orderings, and the behavior of the m plus ith term is symmetric or is equivalent to the ith term, ith entry in the vector field. So just to be clear, that f is a vector valued function, right? So f maps a subset of Rn to Rn. That's clear? I mean, that's...
Yes.
Okay.
So essentially, these side information are some form of like shape constraints you would like to apply to our cost function, right?
Exactly. So
right.
The shape constraint regression paper only talks about convexity and these bounded derivative cases, right? Now, in this case, coordinate-wise monotonicity and coordinate non-negativity is exactly that. It's exactly the equivalent to the bounded derivative. I mean, non-negativity is not exactly the same, but the same kind of relaxation can be applied. Except instead of the partial derivatives, you just take p of x itself. Okay. So set invariance is the more interesting one. That's saying that if my trajectory starts my initial condition, right? So with the differential equation, you always have the dynamics, like x dot is equal to f of x, and you have an initial condition, x of 0 is equal to x naught, or something like that, right? So now set invariance said that if I start in any point in some set B, as in between for all t and like 0 to some capital T on a finite horizon, or even infinite, 0 to infinity, I will remain in this set. Okay, so this is actually a very well studied aspect, but this is nice because it allows us to really add some nice constraints to this. Okay, now we'll talk about the quality of approximation briefly, because again, this is very similar to the earlier result as well, though I've not found a proof for this theorem. But it's similar it's almost identical actually in spirit to the other one, with a few added steps because you have the dynamical system that has to be satisfied. So first, let's define approximate satisfiability. So we have a vector field F. We know that we have some side information S, so it's one of any combination of these 6 things, right? Like it could be P of 0 could be 0, it could be monotonically increasing on the box, and it can always remain on the box, okay? So this basically comes in the form of equalities A equals B and inequalities A less than B, right? Now, what this means is, this is now, if it's delta satisfied, that means instead of A is equal to B, we say that the absolute value of A minus B is less than or equal to D, and that A is less than or equal to B plus delta, some term delta. And so delta in this case is the worst case for over all the possible sort of shape constraints that we have. Okay, so you kind of get that? So instead of exactly satisfying the equalities and inequalities, we allow it to vary by some factor delta. Is that clear?
Oh.
Right?
Yes.
So this theorem now is similar in spirit to the approximation theorem we had before. So what it says is, it says weaker. It says that, look, for any epsilon, delta, and t, you can always find a polynomial vector field which maps omega to Rn, which is the same domain of F, right? F can be anything. It doesn't have to be polynomial. It can be any vector field. But for any epsilon, delta, and t, you will always be able to find a polynomial vector field which has the same domain and range, such that the trajectory starting from the same initial condition. So phi sub f, it's the trajectory, the solution to this the differential equation x dot is equal to f of x, starting with initial condition x naught, right? And phi sub p is the solution to x dot is equal to p of x starting at x naught, right? So these are the trajectories. So they're always close. So the curves always stay close to one another for all time, right? On 0t, and they always remain epsilon close. Okay, and this is a norm. This is like an L2 norm. And the polynomial p also delta satisfies S. Right, so this is a weaker theorem. It doesn't say that the error goes to 0 or anything. It just says you will always be able to find a polynomial which satisfies this epsilon closeness on this time horizon, and which approximately satisfies the side information. Is that clear?
Mm-hmm.
I don't know how they've proved this, but I'm guessing they use something called Grunwald's lemma, which is used to typically show how trajectories stay close to each other. But anyway, I don't want to speculate because I've not seen the proof. It's not in the version of the paper. So now let's take a look at why this is really useful. This really shows how well how useful this stuff is. So the example that the paper uses is the diffusion of a sexually transmitted disease. So X1 is the number of the population of men who've got it, X2 the population of women. And so you've got this quadratic vector field, right? And this is just a degree 2 polynomial. It's quite simple. And you have these unknown coefficients, A1, B1, A2, B2. Okay, so that's basically we're trying to solve for this. Now, if we have this side information, it's 0 at the origin. If the trajectory starts in 0, 1, the 0, 1, 0, 1 box, it'll remain there. And it is always monotonically decreasing on 0, 1. Okay? Mm-hmm. Now, figure A is a true vector field, right? So this is what it looks like. So now, if we don't do it, we just use some data, we get some garbage like this. This is without shape constraints, and a good amount of garbage. I think it's some 600 data points that they've used, which is quite a lot for quadratic thing. It looks like garbage, doesn't it?
Yes.
Right. But now, when you add the side information, now it looks a lot better, doesn't it? It looks very similar to what you saw earlier. Right? So this is really the power and the importance of using side information. Now, what does this mean in the long run? This means that a lot of stuff that is non-linear, right? Like a lot of non-linear things that one would normally use reinforcement learning for, because learning the dynamics is hard, can now be done with this, with provable guarantees. Right? I know I can find a polynomial that's roughly equal to this and which roughly satisfies the shape constraints. I know I'm guaranteed to be able to find that. Okay. And so even if I'm not exactly there, as long as I'm close enough like this is good. This looks quite a bit, figure C looks quite a bit like figure A. And that's really what I'm looking for.
So a quick question.
Yeah.
Where does this side is it something like a domain dependent, or how do we know which side information is relevant?
This should be domain dependent.
Okay.
Right. So this is basically this is side information is entirely sort of the art of engineering, right? So for a walking robot, I know that something will change when the robot hits the ground. I know that I'm going to feel some shock. There will be a different dynamics in lifting up and all of that, right? If I have an air traffic, if I have an autopilot, I have some idea of what it should look like, right? I have some idea, even if I don't know exactly what it may be, depending on all of this. I know that maybe it'll be monotonic in this range. Maybe this set will be invariant. Maybe the vector field is non-negative on this set, that kind of thing. This information I know, right? Because I've seen it, I've observed it. Right. So this is the thing.
Okay.
Yeah. Okay. So that's it. Fairly short presentation, like I said. But it's an interesting tool, and I think it's something that's worth thinking about in the long term. This sort of marriage of algebraic geometry and sort of classical statistical techniques. Okay.
So have also people started to use this in context of control systems, or it is absolutely fresh?
So look, like I said earlier, the system identification idea, right? For linear systems, it's very old. This is nothing new. Okay? And in control systems, sort of the common approach right now is to use POMDP or model-based RL, that kind of thing. Right. So this is kind of new in that sense, but this is very similar in spirit to model-based reinforcement learning. There too, you assume you know something about how the system behaves, right?
Yes. Yes.
So it's like I said, in spirit, it's similar. So what is RL? You basically treat your system as kind of a black box or at best a gray box. And then you use policy gradient or SARSA or whatever to learn a control policy that'll give you some behavior that you want. Okay, so you don't really care about learning the dynamics, you just care about learning the policy. What this approach is you learn the dynamics, or you learn an approximation of the dynamics, and then you learn to control that. And hopefully you'll have, and it's not hopefully, it's well known that you can design controllers that are robust to a good amount of perturbation. So as long as you get the model roughly right, your controller will work. So this is that second approach.
Okay.
All right.
Yeah, I think I'm good. So
any other questions, Prashant? Any questions, any doubts?
Yeah, I'm good. Yeah.
No?
No, yeah, I'm good, I think. Yeah.
Okay, cool. So I guess that's it. So like I said, a bit of a short presentation, but hopefully it was interesting. It was a couple of neat papers that I came across recently, and I thought it'd be fun to talk about them. So who wants to go next?